A simple AC wattmeter. I am Ed, AE7TE, and I want to share something I built. I didn't come up with the idea, but I put it into action and I'm pleased with the results. This meter uses a simple peak reading diode detector to turn an AC waveform into a DC voltage. When it's read across a known impedance, it is possible to know the amount of output power in the circuit. My wattmeter is part of my radio station, capable of measuring the amount of power that a given transmitter puts out. It does not have lab-grade accuracy, but it is good to within 2%. This is the wiring diagram of the wattmeter. It's a very simple circuit and could be built as a starter project for any aspiring builder. The 50 ohm resistor on the left could be an external dummy load, or it can be installed inside the power meter case. That's what I did at first, but I found the excessive heat put off by the resistor started to affect my measurements. Now I use a T-connector to attach to an external 50 ohm load, so heat cannot have an effect on other parts of the meter. It's very important to get accurate measurements of the diode's voltage drop and any resistors that will be in series with the meter. I made labels and placed this information on the outside of the case. For larger power measurements, it's acceptable to use a silicon diode such as a 1N914. For smaller power measurements, use a germanium diode such as 1N34 alpha. Do not use a rectifier diode like 1N4007. These aren't suitable for RF. Here's how this thing works. The RF comes in and heats the 50 ohm dummy load. The diode picks off the positive ends of the voltage and allows current to flow through the capacitor, charging it. When the capacitor reaches the peak voltage of the input signal, minus the diode voltage, it prevents the diode from conducting anymore. The switch selects a resistor to measure this voltage across the meter. The meter displays the current through the resistor, and the 100k ohm resistor allows a drain for the capacitor to ensure the meter has a decently quick response. The capacitor across the meter itself ensures that RF cannot flow through the meter, heating its fragile parts and causing damage. To adapt this to an audio power meter, you would have to change the 50 ohm resistor for 8 ohms and make both capacitors 100 microfarads. We need two formulas to make this into a useful tool. The only indication we get is the meter current. That needs to be changed into a voltage and then a power. Our power will show up in milliwatts. If you want to have the power in watts, simply divide the answer by 1,000. Here's an example of how to use these formulas. When you built the meter, you measured the diode's forward voltage drop, and you also measured the resistance of the series meter resistor. Like I did, you wrote these somewhere where they are easily found. When you make a measurement with the meter, it only gives you a reading in current. First, you need to use the reading of current and the meter's resistor's value to find out how much voltage is sitting at the top of the capacitor. That's the voltage that is making the needle move. Now you have to add the diode voltage, square the result, and multiply by 10. That gives you forward power in milliwatts. A brief demonstration of how the power meter is used. This is a transceiver. It's rated for about 2 watts on the 40 meter band. This is the keying device. This is a dummy load rated at 50 ohms. Maximum power should be about 40 watts. And this is the power meter. I took out the current meter reading and I replaced it with one in RF watts. This can be done with a little bit of math, and it makes things a lot easier. The top line is the 10 watt scale, the bottom line is the 1 watt scale. Makes it a lot easier to have separate calibrations for each scale. So, I'm going to key the transmitter and you will see the amount of power I get. See, it gets a little more than 2 watts. If I was running this thing off batteries, it gets closer to 1.5 watts.